Um, so before we start, let's quickly recap that what were we talking about. Um, so we talk about algamel encryption. In algamel encryption, we said that we are the property of discrete logarithm hard assumption, knowing that solving discrete log problem is a hard assumption, as a difficult thing. So Al-Gamar is another cryptographer that he came up with a very interesting encryption system. So the way that it works is that we said that we would start, we need to have a large prime P, that P has P minus 1 itself, which is an even number, should have a very large prime factor. So we discuss how do we derive that. And then once we get that, we would start to randomly choose a x from 0 to p minus 2, and then we compute the public key to be y equals to, can you guys see my screen?
Yes.
Oh, okay, thanks. Y equals to g to the x, mod p, of course. And then we set the public key to be or prime p or generator g, and then this y, and then the secret key would be p, g, and an x. So we said that it is fine to share this public key because knowing this thing, it is a discrete logarithm problem. Nobody should be able to compute x efficiently. So given that, then we said that in order to encrypt a message M, what we do is we generate a number, random number k from 0 to p minus 2, and then we would compute the ciphertext in this way. We have two numbers as a ciphertext. The first one is g to the k, which is the randomness that we chose. And then for the second part, we multiply m, the message we want to encrypt, to y to the k. So the point is, since we use k randomly, g to the k, is a one-to-one function according to the discrete log problem. So therefore, g to the k is also random value. So then it turns out that which y is j to the x, then this piece over here would perfectly hide the message for us because we are multiplying message to some random value. And then we saw that the decryption is just easy. We would just, if we imagine that this is the A, this is the B, we just do B divided by A to the X, then we check together that we are able to decrypt the message. But today we are going to discuss about a slightly different problem, and that has to do a lot with the security of LYAML encryption system. We said that the LYAML encryption is not secure against chosen ciphertext attacks, which is known as a CCA attack. So in this kind of attack, just like RSA, we give Oracle decryption Oracle access to the attacker. It means that CCA, it means that we provide decryption Oracle. Oops. This one is okay. Our attacker has decryption access to the decryption Oracle. So then then now we will see how our adversary can leverage this decryption Oracle to to decrypt this, to attack the system. So let me set this up. So we have LGML encryption, and then on the other side we have the attacker, right? So gamma encryption would run the keygen, right? And then he would compute the challenge ciphertext, and then the challenge ciphertext is going to be G to the K, and then M times Y to the K, right? And then send the C to A, and says that what is the corresponding M, right? M equals to what? So this is how our adversary can break this algorithm. So we know that adversary can now query different ciphertexts to the Elgamal encryption system because he is given the oracle access. So this is how or A would look like. So our algorithm A or adversary has this information. He knows P for the key, he knows G, he knows Y, and then he knows this, let's call C equals to A and B. He has A and then he has B, right? Now he wants to compute the M. So what our adversary would do is he would do the following in order to attack the system. He would compute, actually we don't have to write the text. He would compute B1 equals to 2 times B mod P. Okay. And then what he would do, he would query the oracle for another ciphertext C prime, which is equal to A times B prime. And so here it comes here. The oracle would see that the encryption would see that, well, C prime is not equal to C, so it is not the challenge ciphertext that he sent to. Therefore, he would decrypt this message and send the corresponding message M prime for this request back to back to the adversary. So imagine, remember here that C is not equal to C prime is not equal to C, because if you look at what is inside C prime, we have G to the R or G to the K, and then here would be 2M Y to the K, and this value is not equal to G to the K and then M Y to the K, right? So these are different, and therefore, according to the rules of the game, or decryption oracle would accept this, query and then provide the answer to the adversary. So you can imagine that once the adversary receives this M prime, so he can compute M equals to M prime divided by 2, right? So essentially what our adversary has done is it's a very simple thing. He took the ciphertext challenge, and he knows that he cannot directly query this challenge again. What he does is that he multiplied 2 to the message part, some value to the message part, to the B part, to the second part. And then you send that corresponding ciphertext, which we call it C prime, to query the oracle. We said that the oracle would accept to respond to this query, and the reason is because the ciphertext is different than the challenge ciphertext. If we look closely, after you multiply 2, then mod P to the B side, then this is the encryption of 2M YK, not M YK, right? This is the encryption of 2M, 2 times M, not M. And once our adversary respond to this answer, then because the attacker knows what was the factor that he multiplied b, it was 2, so he can just divide m by 2, and then he can obtain that a specific message. And therefore you can see that attacker doesn't even have to query some other messages. The moment that he received the challenge with one query, he can break the system and he can always recover the message m. So this is a moment that we need to understand that even though El-Gamal encryption system is look like to be secure under chosen message attack or any other thing, or the moment that we open up this crypto system to the public, a lot of cases, a lot of scenarios, CCA would be is a potential for an attacker to attack some live systems. And we always said that for some crypto system to be used in practice, the best practice is to choose some crypto system that is CCA secure. And it turned out that the El-Gamal system is not CCA secure. So this is something that we need to be careful before we start to use this sort of algorithms. We would come back to discuss about the security of the system. We are not done yet. We just talk about the definition. We just discussed that it is not CCA attack. How about is there any way to prove its security? We would get back to that, but before that, we need to understand some other problem that is called Diffie-Hellman problem. In Diffie-Hellman problem is a way that we can use public key crypto to share a key. Like most of the time, for example, when you connect to gmail.com, your browser would use Diffie-Hellman to share a session key with Gmail server, and then that's how you will start to have secure communication. But again, right now we are talking about the textbook version of Diffie-Hellman. So the typical scenario where the Diffie-Hellman becomes handy is there is a publicly available group, a group with prime P and a generator G that is known to everyone. Most of the time, these groups are already installed in most of the operating systems. So imagine that is given, and we have Alice and Bob that they want to share a key. The way that this algorithm works is that Alice would choose an X randomly from ZP minus 1, and Bob would do the same thing. He would choose a Y randomly from ZP minus 1, and then Alice would compute and send to Bob a capital X, which is equal to G to the X mod P, and at this moment that that Bob received this value, he would also compute and send capital Y equals to G to the Y mod P. And both parties, they have received this value. So let's see what they can do with it. So Bob would receive capital X. He raised capital X mod P. So this is going to be X was G to the X to the power Y. It would be XY mod P. And then Alice received Y. She will raise Y to the power X mod P. And then she will compute G to the X Y mod P. Both sides are going to call this one K, and this is the key K, or sometimes you also get the hash of this to compute the k, and this is the key k that you can use for AES to start to send and receive a large file or start your communication. And you see that the both sides, without even seeing each other, just utilizing the same group, they both share a key. They both engaged into generating a randomness key. A part of the randomness coming from Alice, a part of randomness is coming from Bob. This has a very good property, even though one party doesn't generate a really good randomness in the beginning, X or Y. Let's say Alice is running on an IoT, she cannot really generate a very strong random number. It doesn't matter because maybe Bob is a server and he can get a very good number. Then combination of both of them would get us a very good result. So this is a very interesting problem that Diffie-Hellman brought up on the table, and how two parties that they haven't seen each other would be able to share a key. So we would get to this one later on, just about some words about what is Diffie-Hellman key sharing scheme is, but we are here to discuss about something else. There is a correlation from here to discrete logarithm problem. So we are preparing some understanding in order to prove that gamma, and we need this Diffie-Hellman problem before we can get there. So talking about this reduction, so we have I would say we can reduce Diffie-Hellman problem in polynomial time to the discrete logarithm problem. The input for the Diffie-Hellman problem is, so let me mention something over here, that for the other parties like Eve that is seeing this communication, he can see capital X, he can see capital Y, right? He is not able to derive key k over here because by multiplying x to y, let me draw Eve over here. Eve over here would observe, he knows P, of course, he knows G, he knows capital X, and he knows capital Y. But if he multiplies X to Y, he computes G to the X times G to the Y. He gets G to the X plus Y. This is not equal to J to the XY, right? So Eve, even after observing this communication and obtaining these values, he cannot compute the key k just like the other parties because he needs to have those a small exponent x and y. So we can do this reduction now that is clear. We can say that Diffie-Hellman problem, we have P, we have G, we have capital X, and then we have capital Y. And we want to see how we can reduce this to a discrete logarithm problem. So I think it should be fairly easy for you guys to see. We can send P and G, or conversion function is very easy, and capital X to the discrete logarithm problem. Suppose there is a efficient algorithm A that given on P, G, and capital X, he can output small x such that capital X equals to G to the small x mod P, right? So he compute exactly the exponent that you're looking for. That means that he can solve the discrete logarithm problem. Then we would just return x over here for us, and then we can compute the problem by raising y to the power x, which is equal to g to the xy, right? So if there is such a attacker that can attack the discrete logarithm problem efficiently, and we can solve those things, then that means that we can solve discrete Diffie-Hellman problem. So we know that the discrete logarithm is a hard assumption, so this attacker shouldn't exist. And that implies that Diffie-Hellman is also a hard assumption. So there is a correlation between Diffie-Hellman problem and discrete logarithm problem. Another interesting thing to see over here is that how about the other way around? Can we confirm that these two problems are equivalently hard? So can I do discrete logarithm problem? Can I reduce it in a polynomial time to Diffie-Hellman problem? Who thinks, any idea, guys? Do you think we can do this reduction? So we have already shown how to reduce discrete logarithm problem, the Diffie-Hellman problem, to the discrete logarithm problem. How about the other way around? So the other way around, we receive an input like PG and some capital X, and then we want to compute the small x, and so the problem would be we receive some P, G, and capital X, and then our goal is how to find x. Find x, right? The question is that, do you guys have any idea how we can do this reduction? Right. Right. So the point is, we don't know how to do this reduction yet. So this is yet an open problem. If somebody can prove this, then we can have some comfort zone that the Diffie-Hellman problem and discrete log problems are, equally hard. They're equivalent, but we don't have that. So therefore, all we know that Diffie-Hellman is not harder than discrete logarithm problem, just because of the first reduction that we have here. But it would be fantastic if we had this second proof. But still, it is an open problem. It is a challenge for somebody that thinks that they can come up with this, be the trick over here, so that we make this proof happen. And that would be a very valuable thing to solve. But anyways, so it looked like that we can prove the other way around, but all we have now is that if somebody can solve discrete logarithm problem, then we can also solve the Diffie-Hellman problem. So that is what we know. All right, so we understand the relationship between Diffie-Hellman problem and discrete log problem. So now we can go back to what we've started to discuss, and that is the security of the L-Gammon encryption. So it turns out that we can actually prove that this scheme is secure against an attacker that doesn't have decryption oracle access. So for the CCA, we already showed that chosen ciphertext attack, that attacker can break the system. But we said that how about for the case that we don't provide decryption oracle to the attacker? So we are going to reduce it to the Diffie-Hellman problem. So I don't want to read much from the text. I think the best shot for us is to start to do this reduction. And then these words would be useful for you to later come back and see how that works. But so let me just do the reduction, then we can come back to the text. So what we are trying to do is we are trying to make this reduction happen. So we have a Diffie-Hellman problem. So we know that Diffie-Hellman problem is not harder than discrete logarithm problem. We already have that made that connection. We want to reduce this in a polynomial time to Elgamal encryption. Right? So it is very interesting to see how we can make this conversion happen. So if the point would be, if somebody can break a Elgamal encryption system, that attacker should be able to solve Diffie-Hellman problem. And we know that Diffie-Hellman problem is kind of tied into the discrete logarithm problem as well. So this chain is kind of interesting. So let's see how we can make this happen. So we know that from Diffie-Hellman problem, our input is P and then G and then G to some R and then G to some S. Let me just, instead of X and Y, we are just using R and S here. Just I think I use R and S over here, so I just wanted to make it consistent. I'm sorry that I'm changing the variables. So, and then the goal is to compute at the end of the day some value called G to the RS. Okay, that is our goal. And let's see how we can make that happen. So here comes our conversion from Diffie-Hellman problem to Elgamal problem, and it is very tricky. I want your full attention over here. So we are getting to use this embeddings over here, embedding of a hard problem. So we define our public key to be P, G, and then G to the S. Okay. And then so we have used one of these things, and then we also want to define or challenge ciphertext C to be G to the R and then some alpha. Okay. Let me go ahead and then you will see this alpha is some random value in ZP. That's all it has to be. Suppose we send this value, so we are sending this value. So remember that for an attacker to attack an encryption system, all he needs to know is the public key and a challenge, right? And then we said here that we don't provide Oracle access, so we don't have to answer questions. So we said that this is what it is. If you can break the system, you have enough information to break the system. So now we come over here and develop this algorithm A that, given the public key and ciphertext, he can compute the M. All right, this is the adversary that can break Elgamal encryption. Right, so that is our adversary algorithm A, that given this information, he can break this scheme. And then once we have done so, we show that the answer would be alpha divided by M. So let's see how can this actually work. Remember that the ciphertext is going to be, if I want to write it correctly with more details, the ciphertext is G to the R, right? And then M times y to y to the r, right? Or in another word, is equals to g to the r m, and then y stands for you know that y over here is g to the s, and therefore this is going to be m times g to the power rs, right? This is the and this should be the right ciphertext. So the thing would be here is that we said that this alpha, if we choose it to be some random element from ZP, and if this guy can break the system and recover the M correctly, then the remaining value, because this has to be the valid ciphertext, it has to be G to the power RS. Otherwise, the C is not a valid ciphertext. But in order for it to become, we need to find that whatever message that is that alpha is representing, and if that is the case, then the remaining part, it has to be G to the RS. So that's why we divide alpha, which is this part, by M, then we get G to the RS. So if somebody can really break this ciphertext and return the M, then according to the relationship that we know that it should be in the ciphertext C, then we would be able to recover G to the power RS. And that would be enough for us to show that if somebody claimed that he can break the Gamma crypto system, we can use that very same adversary to solve the Diffie-Hellman problem, right? It is going back to the same statement. Now we can make some statements, and this is our B algorithm. So over here, you see that we have a description of B algorithm, and on the previous page, we also gave the description of A algorithm. So I think this is like a bit more precise way of seeing how this algorithm works. But I think overall, this kind of discussing over here with these pictures, it would help a little bit better to understand those algorithms and see the information flow. So because of this reduction, and we know that discrete Diffie-Hellman problem, we reduced it to the discrete logarithm problem, then we know that it according to this thing, the conclusion that we get is that nobody should be able to break this gamma system, because somebody can break it, then we can solve discrete Diffie-Hellman problem, which is connected to the discrete logarithm problem. So we know that these two are a hard problem. Therefore, this adversary should not exist. So let me write the conclusion that A cannot exist because if it does, then right, is a hard assumption. I'm sorry. Right, so this is our conclusion that after we have this reduction, we show that A cannot exist, this attacker cannot exist, because if it does, then we can solve the Diffie-Hellman problem. But the problem is that we know that the Diffie-Hellman problem is a hard assumption, so it contradicts our assumption in the beginning, and therefore A cannot exist. So you see that the pattern that whenever we want to prove the security of the crypto systems, we are using contradictions, right? We assume that some hard assumption exists, and then after the proof, we show that that is not a hard assumption. The hard assumption that does not exist, and then we contradict our assumption. Therefore, the part that is causing that assumption to be not a hard assumption or not a true assumption should not exist. And over here, you see that with the trick that we do, always we find out that our attacker shouldn't exist. So this is the proof for the LGML encryption system without giving access to the CCA, or without giving access to the Oracle. And you see that for every part, we can't just rely and sit back and saying that, well, it looked like that, LGML system is secure as long as Diffie-Hellman problem or discrete logarithm problem in the first place is safe or is a hard assumption. We can't do that. We have to show very concretely that the moment that somebody can break the system, then we can utilize that information to attack some hard assumption. So the algorithms and everything should be there very precisely, and that is what we call a security proof. So a security proof over here is this algorithm B that whoever now says that they can break LGML, we said, okay, awesome. Then we would interact with this person or algorithm that breaks the algorithm, the LGML encryption, and then we utilize that using algorithm B to solve the Diffie-Hellman problem. So everything should be ready. We can't just assume that, okay, I can imagine that this could happen. No, it has to be there precisely, and that's become a part of the security proof. So just like RSA encryption system, that we saw that it has also a version of signature scheme, LGML encryption system also comes with a corresponding signature scheme. So the key scheme is the key generation is pretty much the same as the LGML encryption, but the signature, and the verification algorithm is a little bit tricky over here. So the assumption is that you want to sign a message M from ZP-1. That it means that your message is let me change my color. Your message is between 1, right, all the way to P-2, right? This could be the domain where you can choose your messages. If your message is bigger than this, that means that you need to go and generate a bigger key. In a key generation, you have to choose a bigger prime P, or you can go back and use a hash function later on, and we would see an example of that. So 2 ways to resolve that. So once we have our message that it has this appropriate length, we can start to do discuss about the signature algorithm. So in order to sign, we need to find a key, a randomness k from ZP-1 star. So remember that this means that ZP star means that the GCD of k and P-1 is 1, right? So be careful with this one. P-1 is not an odd number, it's an even number. So it is saying that you should find a random value key k that is the GCD of that number, and P-1, which is an even number, is 1. So pretty much like k over here has to be an odd number so that happens. But we need to test that. So it looks like that we are going to compute the inverse of k, and that's why we are putting this condition over here. So once you have found that, so we need to compute the r, which is g to the k mod p, of course, and then s is going to be the inverse of k. There we go. And then times m minus rx mod p minus 1. Interesting. So you see that we are doing some computation not on mod p. So this one is they are both on mod p minus 1. Very interesting computation, right? No longer p. So the story is that why do we do that? So remember from Euler assumption that if we take some generator, we raise it to the power p minus 1, the answer that we get is 1, or the quotient class of 1 mod p. Remember that if you get any element, you raise it to the power of order of this group, you get 1. We have p, so we have p minus 1 elements, we don't have 0. So that's why whenever we get any element from p and zp, and then we raise it to the power p minus 1, we get 1. So that means that every time in the crypto computation, whatever value you are going to raise the g to the power of, we can do a mod p minus 1 on the top, and then a mod p over here. Why is it so? Because now you get the logic that if this value is very big, we can just do a p minus 1, mod p minus 1, because we know that anything that is a multiple of p minus 1, then that doesn't matter. This part over here, the whole thing would become 1. So therefore, the maximum, the range of these values from here should be from 0 to p minus 2. So that's how we do the computation on crypto. Efficient computation on crypto. So it looked like that we are going to use this r and s to do something g to the r or g to the s. So we are deriving some formulas over here, so we can already make them shortened to make sure that we replace them with p minus 1. So let's go over them one more time now that we are having an understanding where this p minus 1 is coming from. So we compute r, which is g to the k, and then we compute s, which is inverse of k, and then we get our message minus rx mod p minus 1. Remember, x is our private key, and then r is what we've just computed here. M is the message we want to sign, and k minus 1 we can compute because we choose a k that is we can compute this inverse mod p minus 1. And then to sign the signature is going to be just simply r and s that we have it over here, and these two values are enough to become our signature. And in order to verify the signature, given the public key message m, r, and s, which is our signature, we are going to output 1 if this equality holds true, and otherwise we would reject this message. But let's see if this works. So the verification, let's try it. So the verification says that y to the r to the s should become g to the m. Let's see if it becomes. Suppose that the signature is correct. So y to the r to the s, let's see. Y is our public key, so we know that our public key is g to the x to the power r. And then r, let's replace it. R is over here. We said that is g to the k. So g to the k, and then our s, we have just set it to be this value over here. So k minus 1, and then m minus rs, right? And then this whole thing is mod p. So let's see. From the first part we have g to the xr times. From the other side we get g to the k times k minus 1 times m minus rs. So this two would get cancelled, right? We get g to the xr times from over here we get g to the m times g to the power minus rs, right? So I'm sorry, rx, right? Oh, so you see that g to the xr times g to the power minus rx, they will cancel out each other because we would just sum of them, and that would be 0. So it would be g to the 0, which is equal to be 1, and the result is going to be g to the m. So that is correct, right? So if we do this computation, we are given, when we receive a signature, we want to verify, we know the message, we know the signature, and if this equality is correct, then we can accept and saying that the signature that we receive would pass the verification because according to this computation it is correct. So the way that they design.
Can you explain again? Sorry. Why is it that the k times k minus 1 is cancels out? On your explanation, the second line, the k times the g to the k times, why does that cancel out again?
Oh, this one. This k is the inverse of k, right? K times the inverse of
It's
k.
the inverse. Okay, I thought it was minus 1. Okay, super.
So remember that we can do k time divided by k, right? This becomes 1. So in modular arithmetic, we said that the inverse of a sum number, that remember for RSA, we discussed that D is the inverse of E, right? Because E times D becomes 1 mod n, right? And we had extended Euclidean algorithm. Given E, given phi n, we could go ahead and compute the D, right? So this is the same thing. We go and find the inverse of k, mod p minus 1, and the inverse of tk, we denote it by k minus 1. You can imagine that some other value that we divided by k. And when you multiply these two numbers, the result would be 1. So they cancel out each other. It just look like that you just do division. Okay? And then I think this part should be easy to understand also. So we have g to the xr minus, when you multiply them together, the exponent, you add the exponents, right? Minus xr, which becomes g to the 0, which becomes 1, right? So that part is easy to understand. So when you do this calculation, you will get the result, which is g to the m. And from that, they design the verification to have this formula. Okay? Is this clear now?
Yes, thank you.
All right, so this is very simple, right? I understand that maybe you may wonder that where this value and s, r and s have been computed and things like that. So these are the art of this Gamma guy. This is the way that he has mixed this message and combined, engaged the private key so that he can compute the signature. There is no a step like saying that because of this and that, he computed to be this way. There might be some other way to also combine them, compute the signature, but this is the way that he came up with. So I'm not arguing that this part is the best part. There's no other way that you can frame it. You can come up with some other way, and then maybe your verification would be different. The whole point is to utilize the discrete log problem, do the computation on ZP and come up with a signature. All right, it looked like that we way past your break time. So let's come back after 10:03 so you get fair time for your break time, and then we will continue.